Okay, so welcome to Math 383. This is lecture 31. And so what I want to do today is, finish up the unit on Fourier analysis. We may not do that. We may have to talk a little bit about it in class on Monday. But the goal is to get to Poisson summation today. And this is extremely important for a variety of problems. For us, it's especially important because it was the key ingredient in proving the functional equation for the Riemann zeta function to allow us to extend it to be a function defined for all s and not just real part of s greater than 0, which we were able to get from some cheap extensions. Okay, so I am not going to prove things for the most general class of functions. I'm pretty sure you don't want to see it proven for the most general class of functions. If that is wrong, please see me privately. Okay, I'm going to just take a nice class of functions that have good enough decay that in all situations we really care about, these conditions are met. These are not very severe conditions. You have wonderful games you can play about how can you push things. A function is called to be an L2 if the integral of the absolute value of f squared is finite. I was once on a talk on Fourier series about functions f such that f log squared f is an L2. These hyper technical, and it was a fascinating talk. Loved every moment of it. Right? We're not going to do that here. We're going to deal with very nice simple conditions. So I'm going to say a function f decays like x to the negative a if for all x sufficiently large, all x beyond some x naught, then f of x is less equal to some fixed constant divided by x to the a. Can anybody tell me a value of a that would make them happy? For the decay. I want it to decay like x to the minus a. Give me a value of a that would make you happy. 0. Why would that? So if I take a equals 0, then that would say your function is bounded. There would be no guaranteed decay. Well, if I take -1, then the function is going to be growing. I'm sorry? 2. Why 2? We don't necessarily know that. Just because the function is bounded by 1 over x squared doesn't mean the derivative is bounded by 1 over x. So maybe the function is getting small, but it has a bunch of spikes. And so it could be getting small and have a very small spike where the derivative is quite large, but the function hasn't changed that much. So if I'm integrating from -infinity to infinity, I claim certain values of a are going to be very nice. If you want your function to be integrable, it's got to be decaying at a certain rate. So when is 1 over x to the a integrable? For what values of a will the integral be finite? Two. Can you give me the critical cutoff? If a is what? Greater than 1. If a is 1, you're going to get the logarithm. 1 over x that integrates to the logarithm. So for problems like this, if a is greater than 1, I'm a little bit happy because I have some decay. I can integrate from -infinity to infinity. The result we're going to do is we're going to prove Poisson summation. That will define what the Fourier transform is later, but as long as my functions f prime, and f double prime decay like x to the -1 plus eta for some positive eta, then the sum of f of n, as I range over all integers, is the same as the sum of f hat of n, as I range over all integers. Okay? Now, most functions are going to have decays like this. Question?
Are we assuming that f of x is real value?
Yes.
Periodic?
Over here, I'm not assuming it's periodic. If f is not real valued, of course, you could write it as a real plus an imaginary part, and then things would split, and you could do it for each one.
Yeah, I was thinking about the twice continuous differentiable.
Yep.
Condition.
Yep. And so right now we've got a nice function of just one variable. So for it's think of the function as being real valued. Yes.
Do we need also the first and second?
Right. I'm saying f prime and f double prime all decay like x to the -1 plus eta. So I'm assuming all 3 functions have decay.
But that's not necessary.
So it's not necessary, I think, that they all decay at this rate. There's games you can play in terms of what's the smallest amount of decay that I might need, say, on the second derivative. I'm not going to play games like that. I'm going to just choose something where I assume my functions have reasonable decay, and in the situations of interest, this will all be met. And then this is why you make friends with theorists who will then prove these results in as great generality as possible, and then you just take that off the shelf when you need it. But the main thing is that we have these equalities of sums. The sum of the function at the integers is the same as the Fourier transform. To just give you a sense of how bad things can be, here is a fun function to consider. F of x is n to the 6 times the quantity 1 over n to the 4th minus n minus x in absolute value, if x minus n is less than or equal to 1 over n to the 4th and 0 otherwise. So whenever you see something like this, you should try to get a sense of, well, what does it look like? So let's plot this a little bit. So here is n. I'm not going to draw things to scale. Let's go over a little bit. So here is n plus 1 over n to the 4th, and here's going to be n minus 1 over n to the 4th. When x equals n, what's the value of the function going to be? Nope, n squared. So it's going to be very large. It's going to be n squared when x equals n. When x equals n plus 1 over n to the 4th, what will it be? 0. So at the two endpoints, it's going to go down to 0. So it's going to be a triangle function. What's the absolute value? So when x is greater than n, I'm going to be taking the negative of this. When x is less than n, I'm going to be taking the positive of this. So
this shape is not really like triangular, but
it's a triangle. No, it's a triangle. It's a triangle.
is that a straight
If you're drunk, yes.
line? Yeah.
It's a straight line. This is a triangle function. Okay. So go through and plot this if you're unsure. But when x is less than n, then the absolute value is just the same as the function. When x is greater than n, it's just the negative of that. So it's two straight lines. Okay. And so it is a triangle function. Now, the width of the triangle is getting smaller and smaller and smaller. Can somebody tell me what is the area of the triangle?
No,
1 over n squared. And the reason is the base is 2 over n to the 4th. That's why I'm doing it like this. The base is 2 over n to the 4th. The height is n squared. So the area under this triangle is 1 over n squared. So if I tried to integrate this function, I would actually get that the integral from negative infinity to infinity of f of x dx would be finite. This is a function whose integral is finite. As you go off to infinity, for almost all x's, the function is going to basically be 0. It's only when you get near integers that the function is not 0. And it's going to be spiking up, but as you go further and further down, it's going to be spiking up over smaller and smaller sets. So if you ask, what is the limit as x goes to infinity? Well, the limit doesn't exist. If I send x to infinity through the integers, it's going to go to plus infinity. So if I try to consider certain functions, I'm going to have some trouble. So a good function to look at is, let's let big F of x be the sum, n goes from minus infinity to infinity, of f of x plus n. Is this a periodic function? If I replace x with x plus 1, is this periodic? Yeah, I'm just summing over all the integers n, right? If I increase x by 1, that's just re-indexing the n's that I'm summing over. So this function is going to be periodic. If it exists, this function may not be defined. And so because of the problems f has at the integers, if I take x equals 0 or any integer, big F of 0 is going to be undefined. But if I take any other value of x, it's going to converge. So here is a function that converges for all values of x other than the discrete set of integers, where it's going to be undefined. The function it converges to is basically going to look periodic. Well, if I have a periodic function, I should be thinking about my results from Fourier series. The Fourier series should be converging to the function. If my function is differentiable and continuously, then the Fourier series should be converging. But we first have to know that the function exists. What do you think is preventing this sum from converging? Why isn't the sum converging? I'm sorry? Okay, but so why is the sum not converging? So the function is getting larger at some points. The function is not decaying. What might help us? Those conditions we have, right? I want f to be decaying. If f was decaying like x to the negative 1 plus eta, I wouldn't have any concerns about this, because then I know that the function would converge. I might want to differentiate term by term. If I want to differentiate term by term, I would want the sum of the derivatives to converge. And that's why I have this condition on f prime. And maybe it's not enough to just look at the first derivative. Maybe I need to look at the second derivative at some place, in which case I would like the sum of the second derivatives to exist. And that's why I have the condition on f double prime. That's where these conditions come from. I want to make sure that the sums that I'm working with exist and are well defined. And by assuming some kind of decay properties on f, f prime, f double prime, then these infinite sums will converge. And then I have a hope of using my results from Fourier analysis. So again, you can go through the notes and read step by step. What I want to do in class is I want to give you the high level view. Why are we doing this? Yes.
Large f of 0, isn't it like the sum of like the
large f of 0 would just be this sum over here, the sum of f of n. And for this particular function, it would blow up.
So like it's just
yes. So big F is going to be a periodic function on 0, 1, but it's not always going to have a finite value. It's going to be plus infinity when x equals 0. Yep. And so we want to make sure that we work with objects that exist. And so what we want to do now is we want to prove Poisson summation. So I am not going to go through all of the steps. I will leave some of this for you to do in reading the book. So for example, the book or the notes show that big F of x equals the sum, n goes from minus infinity to infinity, of f of x plus n exists and is periodic. Okay, and this is going to follow from our decay condition. Okay, if we didn't have that decay condition, things could be bad, but we know from results in sequences and series that it's dominated by something that converges. So this is our decay condition plus the comparison test with a p-series. As a number theorist, I hate saying p-series because for me, I want to reserve p for prime. But this is a p-series where p is greater than 1. So here, p equals 1 plus eta is greater than 0, so converges. Okay, so step 1 is to show that f of x exists. Step 2 is to show f prime of x equals the sum, n goes from minus infinity to infinity, of f prime of x plus n. Okay, so show that the sum, n goes from minus n to n, of f prime of x plus n converges to f prime of x. Is it bad that I'm only going from minus big N to big N? So I'll let n, of course, go to infinity. But how bad is it if I truncate the infinite sum and make it finite? Is it a big deal? Why is it not a problem if n is large? Why?
It decays.
Because it decays. So the truncation is fine because the tail is small by our decay condition. So it's okay to truncate as the tail is small by our decay condition. Okay. And so I'm not going to go through the algebra of showing all this. That's in the notes. If you have any questions, please let me know. I'm trying to balance covering material and showing you what we can do with all these results with doing enough steps that you can see what goes on. So again, strongly urge you to go through the proof slowly. If you have questions, email me, let me know. Happy to talk about how to put in all the details. But you should be comfortable from real analysis in showing that these can be differentiated term by term. And this is where our conditions come from. So we know big F is continuous. What else do we know about it? Decays. What else do we know? Periodic. And one more thing, differentiable. So yes, so once we know that it's differentiable, it has to be continuous. So because F is a continuous periodic differentiable function, it's also bounded. So what can we use? We can use Dirichlet's theorem. Right? So we know the following. Big F of x is the sum, n goes from minus infinity to infinity of f of x plus n, and that's going to be the sum, n goes from minus infinity to infinity of big F hat of n e to the 2 pi I n x. So the Fourier series converges pointwise. Okay. So this is why I needed to prove the Dirichlet theorem earlier about pointwise convergence. So I have pointwise convergence. So it's good to remind ourselves because as mathematicians, we often love to overload notation. So here, f hat of n would be the dot product of, so it's integral from 0 to 1 of f of x e to the negative 2 pi I n x dx. So it's the Fourier coefficient of a function on 0, 1. Okay. So this is the Fourier coefficient of f from 0, 1 to r. But we also have the Fourier transform of our function little f from r to r. And that is given by f hat of y is the integral from minus infinity to infinity of f of x e to the negative 2 pi I xy dx. So this is where things are a little bit unfortunate, is we use the hat to denote both the Fourier transform coefficients, the Fourier coefficients of a function on 0, 1, and to denote the Fourier transform. Okay. Okay, so now there hopefully is some connection between all the stuff in play here. We have Dirichlet's theorem, which gives us pointwise convergence. Can anybody give me a good value of x to use for Dirichlet's theorem? What's a good value of x to take? 0, right? Then that would give us big F of 0 is the sum, n goes from minus infinity to infinity of f of n, and then that would be the sum, n goes from minus infinity to infinity of f hat of n times 1. Right? So we almost have what we want. We just have to understand a little bit more what's going on. All right, so Oh, I need another page. I'll come down here. I'll put this up later. So we have f of x is the sum, n goes from minus infinity to infinity, of f of x plus n, right? So f hat of n would be the integral from 0 to 1 of f of x e to the negative 2 pi I n x. All right, well, I'll plug in the series. It's negative infinity to infinity of f of x plus n e to the negative 2 pi I n x dx. You should be fighting a temptation right now. There's something that you want to yell out. I want to do what? You want to switch, right? So you switch. So this is, of course, the same as the sum, n goes from minus infinity to infinity of the integral from 0 to 1, f of x plus n e to the negative 2 pi I n x dx. Why is that true? I'm sorry? So Fubini-sum, why can we use Fubini here? So Fubini, we need the double integral of the absolute value to be finite.
F decays very fast.
F of x decays very fast, and 0, 1 is a finite interval. So basically, we use Fubini here, and we need to use some kind of decay property, right? And because f has decay, and this integral is of finite length, we're going to be fine. So we can justify the interchange. Now, if you think about what's going on, the exponential function is extremely nice. If I increase x by 1, what happens to, I'll just put this up here, e to the 2 pi minus 2 pi I and x is the same as e to the negative 2 pi I. Or did I make a mistake? Oh, I made a small mistake here. I should use a different letter here. I should use the letter M. Why should I use the letter M? It's not the same n as I'm using here. If I'm evaluating f hat at n, I should use a different variable for my summation. And so if I change x by adding m to it, does that change the value of the exponential? No, it's going to be an integer multiple of 2 pi, so it's not going to have any change. So with a little bit of algebra, it turns out that this just becomes the integral from minus infinity to infinity of f of x e to the negative 2 pi I n x dx, which is just f hat of n. And so it turns out that you can replace big F with little f under the hat in this particular situation without any harm. Normally, you cannot do that, right? But what happens here is, if you think about what's going on, each one of these is an integral over a region of length 1, and then you're just putting them all together. So again, I urge you to go through this slowly and do the algebra and see that this really is the integral from minus infinity to infinity. And so this is really just the Fourier transform of little f at n is actually the Fourier coefficient of big F at n. And so now that we have that, if we go back to, oops. I really want that down, okay. So now if we go back to over here, it turns out that this is equal to the sum, n goes from minus infinity to infinity, of f hat of n. And done. So that's a proof of Poisson summation. So we have the sum of f of n is the sum of f hat of n. You look confused.
Yeah, it's okay.
Okay.
It's a very common.
Okay, so this gives us Poisson summation, and now you can go back and you can show that the identity I claimed for the omega function or the theta function, depending on which one you want to look at, you can now show that that's true. And that follows from Poisson summation. Okay. So what I want to do now is talk a little bit about applications of what we've done to probability. And so the first is, has everybody seen the basics of probability? A density is non-negative, it integrates to 1. The probability you take on a value between A and B is the integral under the curve from A to B. Is everybody comfortable at this level? Okay, that's all we need. All right, comfortable at this level. If not, please speak up. You will not be the only one. All right, so if I give you two variables, let's say, xk with density f sub k, we can consider x1 plus x2. And we can ask, what is the density of x1 plus x2? There's a lot of ways to do this. Informally, I claim the density of x1 plus x2 of little x would be the integral from minus infinity to infinity of little f x1 of t f x2 of x minus t dt. And one way to see why this is true is if the first random variable is t, and I want the sum to be x, then the second one has to be the value x minus t. If you want to do this a little bit more rigorously, how many of you are taking or have taken it? So if you've seen CDFs, you can do the CDF method. I can look at the cumulative distribution function for x1 plus x2. That means I want the probability I take on a value at most x. Yes?
Sorry, just additionally, why do you like under the line?
So it's to let you know that it's a capital letter. So this is the notation. They sometimes talk about like bold blackboard and whatnot. It's to just let you know very clearly this is a capital letter, not a lowercase letter. So we use capital letters for random variables. We use lowercase letters for their values. So if I want this, this would be the probability that x1 plus x2 is at most little x. So then that would be the integral. X1 goes from minus infinity to infinity. F x1 of, I'll use t here. And now, for the second one, x2 can go from minus infinity. How large could the second variable be if I want the sum to be at most x and the first one is t? X minus t. And then I would have f of x2 of, I'll call it x2, dx2, and then dt. So this would be a way of writing down the cumulative distribution function for the random variable x1 plus x2. And now, how do you get the probability density from the cumulative distribution function? If you haven't done probability, don't worry about this. I'm just trying to be a little bit more rigorous for people who've taken probability. You get the density by taking the derivative. Well, over here, I want to just basically take the derivative. Okay, this is going to be the integral t goes from minus infinity to infinity, f x1 of t. And then the second one, it's going to be the antiderivative of the second variable at x minus t minus its value at negative infinity. Okay, well, what's its value at negative infinity? That's just 0. So I would have dx2 dt. And now I want to take the derivative of this with respect to x. Well, if I take the derivative, you want to pass the derivative through the integral. And oh, sorry, this should not be a dx2. Thank you. That should be gone at this point. And so now we want to take the derivative with respect to x. And so when we take the derivative with respect to x, it doesn't hit the first density. And the derivative of big f of x2 with respect to x is just going to be little f of x2 at that point. And when you take the derivative, that's going to give you back that formula we started with. So we've seen convolutions before. We saw convolutions when we were doing the Fourier theorem and the Dirichlet theorem, when we had these approximations to the identities. And I tried to motivate them by saying, look at it as, if we looked at the integral of f of x times an of x, okay, that makes sense that it's just going to give us f of 0. But we could really write that as an of 0 minus x, and that led us to integrals like this. This is an extremely important operation called convolution. We call this convolution. And we'll write, f convolved with g of x is equal to the integral minus infinity to infinity of f of t g of x minus t dt. And with a little bit of algebra, that's the same as g convolved with f. And if these are probability distributions, this is going to give you the density of the sum. So it turns out that we can do a lot with this. So it's always a question of what do you want to study? So a big thing to study is what's called moment generating functions. What do you think a moment generating function gives you? Moments, right? Every now and then we have a good name in mathematics, right? There is a reason why secant goes with 1 over cosine and cosecant goes with 1 over sine. I don't like it, but at least there is a reason. Right? Moment generating functions give you moments. We'll mostly focus on the continuous case. If I give you some density f of x, I'm going to multiply by e to the tx, and I'm going to do that integral, and I'm going to call that my moment generating function of the random variable x with density little f evaluated at the point t. If you've seen normal generating functions, they're essentially the same under a transformation of variables, a logarithmic change. What is your first concern when I write down the moment generating function? Does it converge? Do you think that there could be some issues with convergence? Why? Yeah, e to the tx. Depending on what t is, one of the directions x moves, this is going to become very large. So it turns out for a lot of things to work, we need the moment generating function to exist for t in a neighborhood of the origin, a neighborhood of 0. And for a lot of functions, this just doesn't exist. The Cauchy distribution is one of them. There's lots of densities that don't exist. There is, however, a very nice modification of the moment generating function, which we will see, which always exists. And it's much better to work with objects that exist than objects that don't exist. Okay. The moment generating function has a lot of properties. So so I'm not sure if I explicitly said this. The kth moment of a random variable is just integrating x to the k times the density. And the hope is that if I know the moments of a distribution, then I should know the distribution. This is similar to if I know the Taylor coefficients of a function, I should know the function. What have we learned early in the semester? Not the case. And it's not the case here as well. Just because you know the moments does not mean that you know the density. What we need to know is a sequence of moments that accumulates. And now you can begin to see why this is coming into a class in complex analysis. One of my favorite theorems is the accumulation theorem. If you have a function which is 0 on a set of points that accumulates inside the set where the function is holomorphic, then the function is identically 0. Or equivalently, if you have two functions that are equal along such a sequence, then the two functions are identical. This gives us a way to uniquely determine sometimes when something happens. And so there's a bunch of properties of the moment generating function. You should do the algebra and you should prove these various things. So you should be able to prove lots of things. I'm going to concentrate on like 3 and 4, and I'll just give, I guess it's 3. I didn't label the second one as 4. The moment generating function of the sum is the product of the moment generating functions. Does that remind you of any relationship? Exponential, logarithm, something like that going on. So let's just do that. So this will be proof of 3. So here, we call the moment generating function of x at t is the expected value of e to the tx, which means it's the integral from minus infinity to infinity of e to the tx times the density. Okay. So now, if I want to calculate the moment generating function of x1 plus x2 at t, that's going to be the expected value of e to the t x1 plus x2. And I need to compute this. So we are at the part of the semester where we're doing applications of complex analysis. So if any of this stuff is on the exam, it would be in a section where it might be choose one of the following problems to do. I'm not going to give you anything that requires you to know probability to do an exam problem in this. Now, I may give you a simple problem involving this where you don't need to know a course in probability. But there's going to be nothing in the class where if I've made an advanced comment on probability that's useful, that's great, but you're not going to have to understand that for any exam questions. I just want you to have a sense of how things can be used. I want to calculate the expected value. So what does that mean? So I need to calculate what is the probability of this happening. And here I'm going to assume the variables x1 and x2 are independent. So again, if you haven't seen a lot of probability right now, don't be worried right now. I'm just trying to show for people who've seen some stuff. So this would be the integral minus infinity to infinity, the integral minus infinity to infinity, e to the t x1 plus x2. And then because they're independent, the probability that I have a pair x1, x2 is just the product of the probabilities. If they weren't independent, then I would have f of x1 comma x2, some strange joint density. But because it's like this, I will now, everything splits nicely, and this is just the integral from minus infinity to infinity, e to the t x1, f x1, x1, dx1, and then I do the same thing, but now I have, instead of x1, I'm now going to have x2. E to the t x2, f x2, x2 dx2, and this is just the moment generating function of x1 at t, and this is the moment generating function of x2 at t. So the reason for the miracle is the exponential function. The exponential of a sum is the product of the exponentials, and that's why the moment generating function of the sum becomes the product. Yes?
I'm confused what the double interval came from.
So I'm calculating the expected value. So again, if you haven't done probability, don't worry about this. I'm just trying to do some motivation. I need to calculate what's the probability that x1 plus x2 takes on given values. So one possibility is I know x1 and x2 range over all points in the plane. And for each point, I ask, what's the probability I chose that pair x1, x2? And this is just some basic probability. It's going to just be the product of the probabilities of each one. More generally, I would have some joint density function of x1 and x2. And if I'm independent, the joint density function is going to split as a product. So this is just, I know there's a lot of people in this class who have taken probability. And so I wanted to just put in a few remarks for those of you who've seen probability as to how complex analysis can be used. If you haven't seen probability, don't be worried about this. Or if you want to be worried about this, talk to me and I'm happy to go into greater detail and go through all the steps. But I just want to give a quick sense of how all this comes into play. From this, we get that the moment generating function of a sum is the product of the moment generating functions. And then, of course, if we had just more summons, it would just be more products. The second property is the one that I do on the right-hand side. If I change variables and I look at the moment generating function of alpha x plus beta, it's very nicely related to the moment generating function of x. It's e to the beta t times the moment generating function at alpha t. And again, it's just some algebra to go through and see that this is the case. I strongly urge you to roll up your sleeves and do the algebra. And that's the best way to understand what's going on. If you go through and you do that, and the algebra is listed here, you'll see at the end of the day, the result follows. What this allows us to do is say, look, if I have a nice probability distribution without loss of generality, let me translate it so that it has mean 0. And if I have a nice distribution that has a finite variance, let me rescale things so that the variance is 1. So the first thing is by choosing by choosing beta appropriately, I can adjust it so that it has mean 0. And then by choosing alpha, I can adjust so that it has variance 1. If I have a distribution that has finite moments without loss of generality, I can always assume the mean is 0 and the variance is 1. It's not until you get to the third moment or the fourth moment, if your distribution is symmetric about 0, that you actually start to see the shape of the distribution. All nice densities can be adjusted to have mean 0, variance 1 if their moments are finite. So you don't start seeing the shape of what's happening until you get to the third or the fourth moment.
Why do you need the moments to be finite to do the
Well, I mean, if the moments are not finite, I can't adjust the Cauchy distribution to have variance 1. Because the Cauchy distribution has infinite variance. So if I want to assume that my random variable has mean 0 and variance 1, I need to have finite mean and finite variance. But not every distribution will have finite mean and finite variance. And so we're going to see shortly the central limit theorem. It's going to break down for things like the Cauchy distribution. Now, there are analogs of the central limit theorem that do work for things like the Cauchy distribution. Instead of looking at the mean, you can look at the median. And again, if you're interested, always happy to chat about something like that. So at some point in your life, you should be aware of existence of functions like this. So here are two functions, f1 of x and f2 of x is f1 of x times 1 plus the sine of 2 pi log x. And yes, there is logic behind these functions as to why someone would choose to write these down, right? It turns out these two functions have the same integral moments. I believe they even have the same half integral moments, but not beyond half integral moments. So as a nice exercise, try to calculate the moments of these distributions if you can. Or if you can't, at least show that they have the same integer moments. So I may not be able to compute them, but I can show that they both equal the same quantity when I put in an integer. So 3 halves, 7 halves. If you look at the 7 halves moments, I believe they're the same for this, but not the 7/3 moment or the 7/5 moment.
So it works for integral moments.
So for these two densities, they have the same integral moments. I believe they also have the same half integral moments. I would have to double check that, but I'm pretty sure.
You said like a function is equal to its, like if it's uniquely defined by its moments, if the moments accumulate.
So if I give you a sequence of moments that accumulates, then that uniquely determines the density.
Why can you say that even though like these functions are not necessarily like we're not in complex analysis, right?
Correct. But we want to be. We want to be in complex analysis whenever possible. You know, we're pissed off that Wednesday there's no class, right? You know, this is not a cause of Thanksgiving. You know, whenever possible, you want to convert things to complex analysis. So over here, I'm only looking at things that are real valued, right? It's the same thing as studying the prime number theorem. It makes it easier sometimes to convert to complex analysis and to be able to use those formulas and those theorems. And so here, when I'm looking at these densities, these are two different densities that have the same sequence of moments. And so it is not enough to know the sequence of moments to uniquely determine the function. I need more.
Is it true that if two density functions have the same moment, then one have to be the other times something? Because
That I don't know. That I don't know. Well, I mean, the answer is yes, because I can always just define it as, you know,
So,
yeah, you give me functions f and g, I can write g as f of x times g over f of x.
okay.
Right? So I can always write one as a multiple of the other. It's just how nice is that going to be? You know, what we saw in the Weierstrass products is if you have the same zeros as another function and you're holomorphic, then you have to be a multiple of an exponential of a holomorphic function. So not only are they multiples, but it's a very nice multiple.
Also,
So the question is, do you have something nice like that? Okay. So here is zooming in on our function e to the negative 1 over x squared. Yeah, this should be one of your go-to examples of how bad life can be, right? You're 0, your speed is 0, your acceleration is 0, your jerk is 0, your snap, crackle, and pop are 0. Every derivative at the origin is 0, and yet somehow you move, right? It's a good exercise to use L'Hopital's rule to show that this function has all of its Taylor series coefficients 0, but is not the 0 function. It's the challenge of dealing with stuff like this that makes analysis so difficult. Okay, so now characteristic functions. So I talked about the moment generating function, which doesn't always exist, right? And so we said that the moment generating function of t is the integral from minus infinity to infinity of f of x e to the negative 2, I'm sorry, e to the tx dx. Okay. And why is this function not necessarily existing? What's the problem? You're missing an I, right? The exponential function is growing. So let's look at what's called the characteristic function, which will be the moment generating function at it. And now, will this exist? Yes, f is a probability distribution. The integral of f is 1. F is non-negative. So if I give you a probability distribution, then clearly this is going to exist. So we go from the moment generating function, which may not exist for many values of t, to the characteristic function, which exists for all values of t. This is a good trade. So this is the characteristic function. What do you notice about the right-hand side? Yes.
If two probabilities then they're the same
You want to basically say, I have. So let me get back to that after we identify what is this. Does anybody recognize what we have on the right-hand side?
Well, it's missing a 2 pi something.
Well, is it really missing, or can we just quickly rewrite it as e to the negative 2 pi it negative x over 2 pi, right? Now it's no longer missing. And now it's just f hat of negative, oh, except I don't want to write it like this, right? I want to write it as negative t over 2 pi times x. So really, the characteristic function is the Fourier transform, but we're just changing a little bit where we're evaluating it. And this is the age-old dilemma of where do you put the negative signs? Where do you put the 2 pi's? How many of you have done rationalized MKS? The speed of light is 1, the gravitational constant is 1. You normalize as many constants to 1 as you can, so you don't have to worry about things. I hate those units, because when I look at equations, all the physics is now missing. The rationalized mathematical units is pi equals 2 pi equals e equals 1. Sometimes they go so far as to include the square root of 2 as well. I mean, I think that's pushing it a little bit. But just up to factors of 2 pi, up to factors of, this is what's going on. So the characteristic function is essentially just the Fourier transform. And so then your question becomes, if two functions have the same Fourier transform, are they the same function? Or equivalently, if my Fourier transform is identically 0, then must that be coming from the 0 function? Okay, so this is a good place to leave. So we will finish stuff like this, and we'll get to the characteristic function of the standard normal. So I'll let you think about this for Monday. Can you calculate the characteristic function of the standard normal? So that means you have to integrate from negative infinity to infinity of e to the negative x squared over 2 e to the itx dx. Okay, this is not the standard normal. I'm making things a little bit nicer. You can put in the 1 over square root of 2 pi outside. Okay, so can you evaluate that integral? So I will let you think about that for Monday. All right.